I did a little bit of that part. I don't remember the part that said like just in this one thing.
And whoops, you just lied. I forgot it was a square root. Okay. I want to fail. How much is like percentage off? And I'll see you at 9 and a 10. I'm pretty sure they're practicing. Yeah, I'm gonna fail. Yeah. Oh. Five. It's just
One five.
How? It's just July. You're not.
So you won't get it.
What's your birthday? When? Yesterday.
You just kidding.
It was you 2 days. No, June 20th. I didn't even know you June 20th. That's 20 days. That's 20 days after my mom. I mean, over 21st. What? August 21st. That already passed. I wrote it down in my notes. Thank you. I have an election. August or August. Wait, what? What you do? 2007. I'm freshly 18 though. 2006. Wait, you're you're about to turn 19. How old are you? I just turned 8.
I'm too good.
You're not a professional, but you're not a professional.
Yeah.
Crazy. Oh, boy, you're what's that? So it's freaking explanation. Point solutions. Point solution.
I also. I'm kind of scared.
Wait, actually, I'm kind of worried. I'm not. No, bro.
Okay, I got mad.
Yo, let there be a limit.
Not something else.
Let's do that. Who are they? Oh, you're doing fast for them.
Yeah.
Proper notation. No. Yeah, probably put like that sign. What was your notation?
I do that. I don't know what's fun, but I'll do this small. Yeah.
Play your team. I didn't even log in there. What is this? Log in, bro. Log in. Your smile faded, bro. Smile disappeared. It's mostly because I can't log into this. Box there? Bach? Johann Sebastian Bach? It's like,
You know what I'd say?
I'm doing ATV theory and I hate Bach. Like Bach is a good.
No, I like.
My favorite is overrated. Yeah, Mozart is overrated. My favorite composer is freaking Beethoven. Beethoven. What? That's like a generic. Ludwig van Beethoven. On the bass. We're just really likes the third. Well, Mozart breaks too many rules. Like he does parallel fifths. He doesn't voice lead correctly. Oh, you got to get there's a morning.
Any questions for this time? Everybody's good? Okay, so just a reminder that the one bonus point will be due this Friday. Okay, and I know we just finished our midterm one, right? Mission 2 is actually coming up very soon. Okay, so we're going to do the chapter 15 next week, right? And then the following week will be the reviewing week like we did for the midterm one. Okay, and then we'll do midterm 2. So it is not very far away, it's actually very near. Okay, so I think everybody should get more prepared for midterm 2. I think basically right now everybody should have some experience. You should know what's actually the most efficient way to prepare this course now. Okay. You understand, right? I'm going to understand everything we are in this room. So you can actually use minimum time and effort when you go home. Okay. And the question we went through, they are all extremely important. Very likely you're going to see that again when you do your real midterm. Okay. Make sure you do your first exam before midterm 2. Okay. Time yourself. Okay. Time matters a lot for your midterm 2. Okay. And we're going to do a lot of practice during the lecture, right? Like the one we posted right now. Okay. Try to participate as much as you can because you realize that if you know how to do this, if you can recognize the pattern of the chapter 13, 14, and 15, you may actually find midterm 2 is actually the easiest one to prepare. Okay, so the key is actually recognize the pattern, right? And the pattern is actually very simple. You need to know what kind of solution that you have. You need to know what equation that you need to use. Okay? So that's why you're going to see a lot of this point solution question. It's really asking you, okay, what equation did you actually use? Okay, we keep practicing this since actually last week. Okay, so try to do this as much as you can, okay? So this question actually asks you about how to calculate the pH of a 0.5N HPR solution, right? So first thing you ask yourself is, what kind of solution I have? Yes, strong acid, okay? And then you should see that I try to de-emphasize the name of the chemical, right? I always ask you to answer is strong acid, strong base, weak acid, weak base, or water, right? Because I don't really care what specific chemical it is. As long as I know it belongs to which categories, I know what equation to use. Okay, and that's the things that you should do the same. Okay, don't get scared when you see the chemical formula. All you need to do is actually translate into something that we're familiar. Only 5 solutions you can have for midterm 2. Okay, so here since we have what? Strong acid, right? Therefore, you know the total concentration will equal to your acid concentration. Okay, so once you know that, I think that's actually the equation number 1, right? So you know equation number 1 is the things you need. And once you got your total concentration to calculate pH, you only need to simple to the next row of that total concentration, which is equation number 5, right? So 1 and 5 are the only 2 equations that you need. So much like this. Okay. Very simple. Okay. So I think everybody doesn't have problem with that. Okay, so let's do something else. How about this? Okay, so let's look at this question, right? So what kind of solution do we have? With acid, right? So you don't really care about what that HF is, right? That's what you know, it doesn't belong to big seven. It's actually weak acid. Okay, so this is weak acid, and we know we should also start from the calculating the photon concentration using square root of weak acid concentration as its Ka, right? Which is your equation number 2 here. Once you got your photon concentration, then you do the next log to get your pH. Okay, so that's actually how you should solve a question like this when you do your quiz for chapter 13. Okay, it should be very straightforward. Okay, so don't overcomplicate your life. Okay, just do that, then you get the answer correctly. Okay. How about this? Thank you.
I'm the most thing ever described me. Every time. I thought you were running through them. I wish you know it's the real thing.
See, this is a part that all the field fails. This is a question that, you know, here most of the students, right? So what is actually the things we're actually talking about? What is actually solution? Okay, let's talk about the chemical formula, all right? What is the chemical formula of the solution that you want to actually deal with? Which one? There are actually two chemical formula over there, right? One is NH4Cl, the other one is NH3. Which one is your target? NH4Cl, right? And you see these things, NH3, right? And they give you Kb, right? But is there something that you want? It's not, right? The solution that you want to know here is what? NH4Cl. It's not NH3, okay? But many students, when they see the question have this Kb values, they automatically think the solution they have is weak base. Okay, let's actually replicate the book. Okay, that's not how you do it. You should know exactly what you want, right? Science is actually very rigorous. If they look different, they are different. So NH4Cl and NH3, they are two different things. Okay, And if you read your question carefully, you know you don't want N at 3. That means actually the solution you have cannot be a weak-based solution. Does that make sense to everybody? Because what it really implies that you don't have a weak-based solution, you have one weak acid solution, because the species that lives in the question will be its conjugated acid. Does that make sense? So if just look at carefully about your question, look at the species they want to solve its pH. It is actually not exactly the same species that provide Kb, but you know they are conjugated acid-base pairs. Meaning that if they provide Kb in your questions, the solution you're going to have will be a weak acid solution. Everybody got what I say? This is type of question that I see so many students fail. Okay. However, let's say we get through the barrier. Okay. We did successfully in our step number 1, which we recognize the solution we have is a weak acid solution. Okay. Then we will know we actually first calculate the photon concentration, right? Since it's weak acid, and you know your photon concentration equals square root of weak acid concentration times your Ka. Okay, so you need to use the equation. Then you realize that I don't have Ka, right? In that question, you don't have Ka, right? But we know Ka times Kb equals to your Kw, right? Therefore, you can actually calculate your Ka using that equation, which is equation number 8, right? Okay, so if once you get your photon concentration, then everything goes back to normal, right? Negative log of that photon concentration, you get your pH. Therefore, the answer will be what? 2, 5, and 8. Okay. I hope by now you should see what I could say that in order to succeed in midterm 2, you always need to ask what kind of solution that you have. Because you know that calculating wise is very, very simple. Okay. But that's a part, you know, students actually fail to see. Therefore, most of them fail badly for midterm 2. Okay. So do practice this a lot, okay? All the things we miss here is simply for that purpose. Okay? Okay, any questions so far? Cool. So right, so this one is actually the one that gives you the Kb inside the question. Okay, but the pH, they want to tell us like the pH of NH4, CF, right? I hope by now that you see this guy, this halide group, right? Once it's thrown into water, they dissociate. Okay, it becomes what? These two species, right? So CO minus the conjugated base of HCl, right? And we learned that if you are conjugated base of a strong acid, itself is neutral. Okay, so if you know what I'm talking about, go watch the video last week. We actually spent quite some time talking about this. Okay, the conjugated partner of your strong acid or strong base, they're all neutral. Okay, so if you see something like this, right, once it dissociates, if you see CO minus, you know this one is neutral, right? It means your pH will actually coming from this guy, right? And then NH4 plus, if you compare to this NH3, you should see that it has one extra H plus, right? NH3 plus H plus is an NH4 plus. Therefore, you know that NH4 plus is the conjugated acid of NH3. Where NH3, you know, is a weak base. Okay, therefore, you know this is actually a NH4 plus is actually a conjugated acid of NH3. Therefore, the solution you have is actually a NH4 plus solution, which is a weak acid solution. Okay, is that clear? So I want to actually give you some quick summary of all the things that we see. How do you know you have a strong acid? Yes, you memorize the big set, right? How do you know you have strong base? It's actually 1A, 2A element with oxide, hydroxide or hydrogen. Right? This is how you actually distinguish you have a strong acid or strong base, right? How do you know you have a weak base? Amine, very good. NH3, okay, or you have different substitution, RNH2 or R2NH or R3N. All those things is actually your weak base. Okay, you must become an expert of that. Every time you see an equation, you see NH2 inside your formula, you must recognize it is amine, because amine is actually the part that confuses you guys the most. But that is actually the one that show up all the time. Okay, so amine, every time you see amine, we base. Okay? How about other things? All other things besides amine, we can consider it as weak acid. Okay? So it's actually very easy to tell when you have strong acid, strong base. Weak base is basically your amine, right? And weak acid is pretty much all the remaining things. Okay, of course, all differences that are not related to insights. It's related to how you actually handle the two. Okay, there are other weak base. Okay, but in this courses, it was designed away, and we don't really talk about other weak bases. Okay, I mean, it's actually one of the most abundant weak base that we use in the lab. Okay, so that's how you tell what solution they have. Okay, and I really need everybody to have the ability to see this. Okay, because only after you have the ability, you'll realize, okay, B10 is actually much easier to prepare. Okay.
I think one more question for the solution. So the answer to this will be A, right? Let's make sure everybody is actually on the same page. Okay.
Okay, so let's do this one again. Okay, what kind of solution do we have? What kind of solution do we have? It is a buffer. Okay. But how to know it is a buffer? So if a solution has coexistence of conjugated acid and base. Okay, every time you see things, you have conjugated acid and base inside a solution. It is a buffer. Okay, how do we calculate pH of buffer? HH equation. Only one equation, which is your equation number 9. Right, equation number 9 is your HH equation. Okay, so I have a feeling that you guys haven't been able to identify this is the buffer solution. Because apparently, like everybody has a much slower response compared to the previous ones that we actually went through, right? So how do we actually see we have a buffer? So if you read this question carefully, right? What are the things that are inside your solution? HF and NaF, right? HF is a weak acid, right? And NaF is what? It is a salt. Once it is salty, it becomes Na plus and F minus, right? Na plus is the conjugated acid of NaOH, right? So it's neutral. So you can throw it away. So it remains F minus. Okay, so you have SF and F minus inside your solution. And you should be able to see that SF and F minus, they are conjugated acid and base, right? Therefore, you actually have a buffer. And if you have a buffer, then all the thing you do is actually very simple, right? So for your HH equation, pH equals to pKa, negative log, conjugated acid concentration over base concentration. And that's it. Okay? So, any question for this? Do you guys know how to actually determine whether you have a buffer solution now? Okay, so let me emphasize this again because that's the topic we're going to go through over and over again today. I want to make sure you know these things. Okay. When are we going to have buffer? When we have conjugated acid and base coexisting inside your solution. Okay. So this one actually demonstrates a typical question I'm going to see. Okay, if I throw in a weak acid and is conjugated base, typically you're going to see a form of salt, right? It's NaF. Okay. You throw these two things in, then you have conjugated acid base coexisting inside your solution. Therefore, you have a buffer. Okay, so this is actually one way to create a situation, which is the most commonly used way to generate your buffer. Okay. However, the things I'm going to say is actually very important, so listen very carefully. There are other ways to generate a buffer. For example, I have 10 mole of weak acid, let's say 10 okay? And then I mix them with 5 mole of NaOH, which is a strong base, right? So whenever weak acid mixed with a strong base, what's going to happen? And you actually have a weak acid strong base coexisting. You cannot. Okay. So remember last lecture we said for strong acid, strong base, they are single-minded, right? They don't allow other species to exist. Right? So if I'm a strong base, I see a weak acid. What I will do is I'm going to kill every single acid that I see. Right? However, who is actually more abundant in the things we just described? weak acid, right? That means even the strong base, it consumes all of it. There will be still plenty of weak acid remains, right? Okay. So what happens when I have a strong base? I kill one of the, actually not kill, okay, I actually sacrifice myself and then kill it, right? So once I interact with a weak acid, then what do I generate? Think about this HA, right? Weak acid HA into a strong base, OH minus, right? So the OH minus will actually get the proton from your HA, okay, to form water, right? But what remains? Once you HA give out your proton, we be able to generate the A minus. Everybody see what I say? Okay, the strong base OH minus when interact with your weak acid HA is going to pull out the H plus from your HA. At the same time, generate what? A minus. Okay, and this thing will always happen. Okay. So now, the situation you are going to end up with will be you still have plenty of HA inside your solution, right? But half the length will become A minus. So you get back to a situation you have coexistence of HA and A minus. Therefore, you're going to have a buffer again. Everybody follow what I say? This is actually the core, the concept we want to actually learn today. Okay? So everybody's fine so far? Okay. So the situation I described is what? I have more weak acid than my strong base, right? Okay. Now we want to go to another situation. If I have the same amount weak acid and strong base, okay, the same amount weak acid and strong base, what am I going to end up with? Think about it. Okay, HA plus OH minus. Okay, right now they have the same amount. What am I going to get at the end? It's not neutral. So what?
Can you repeat?
If I have the same amount HA with acid, next with strong base OH minus. Okay, the same amount. Okay. What will I end up with? Once my system reaches equilibrium, right? What kind of solution am I going to get? A weak phase solution. Because HA plus OH minus, right, is the same amount, right? All the OH minus will scrap all the proton from HA. Therefore, you don't have HA right now in your solution. All you have is A minus, right, which is a conjugated base of your weak acid, which makes it a weak phase solution too, right? So if you have the same amount of weak acid, strong base, then you end up with a weak phase solution. Okay? Everybody follow? Good. So we go from more weak acid versus strong base, right? And then we go to the same amount, right? Let's push it further. If right now I have more strong base to add it into a weak acid solution, what kind of solution are you going to have? The more strong base than weak acid, okay? I'm going to have a what kind of solution? Okay, what are going to remain? What's the things you're going to have? All the weak acid will be killed, right? So you're going to produce a lot of A minus. Okay, but at the same time, you still have a lot of strong base inside your solutions, right? So you end up with a situation that you have a bunch of strong base, bunch of weak base inside your solution. Which one is going to dictate your pH? Strong base. Therefore, you just need to actually calculate what is like your OH minus concentration. Then you can actually calculate your pH, pOH, then your pH. Okay? So the things I say is actually the core of titration. Okay, which we're going to go through very quickly later on, okay? But I hope that everybody now can see this very important concept, because if you see this concept, titration is actually very easy for you. Okay? So you need to actually know what kind of solution that you have, right? So let's say we're starting from a weak acid solution. We have a bunch of H8. Okay. Then since the weak acid, everybody knows how to calculate pH, right? Photon concentration equals square root of weak acid concentration times Ka. That's actually the first type solution of the type, right? And then you can give a small amount of strong base. Okay, so all those OH minus, all those strong base will be consumed by your weak acid. Right, so under that situation, you not only have your weak acid HA, you're also going to have its conjugated base A minus. Right, so this setup will actually make your solution become a proper solution. Right, so that is actually what you're going to have. You have a less amount of strong base into a high abundance of weak acid solution. Okay. And this will continue until you hit a point that you have equal amount of weak acid strong base. Right. In this case, all the weak acid will be consumed with your strong base. Okay, the same thing, strong base will be consumed by weak acid too. So end up with a solution contains a bunch of A minus, which is the weak base solution. Okay. And but if you keep adding in your strong base, then you end up with a strong base solution at the very end. Okay. So the things we describe actually describe 4 different situations, right? So which we're going to use 4 different zones to describe each individual conditions. Okay. So your job is that every time you see a titration questions, you want to ask yourself, which zone am I? Okay. So because if you know your zone, you will know what kind of solution that you have. If you know what kind of solution that you have, you know what equation to use already. Okay, so that is actually the key. Okay, you really need to know your zone for chapter 14. Okay, so what we're going to do today is actually to tell you how to distinguish which zone you are, so that you will know what equation to use. Okay? So, that's actually a very long introduction for today's lecture. Okay, any questions for this introduction? Everybody follow this? Okay, if not, then really try to understand this. Because once you understand this, chapter 14 becomes very simple. Okay? This is actually the most difficult part for chapter 14 for students. Okay, so for chapter 14, we're going to talk about this thing called titration. Do you guys know the titration instrument yet? Not yet? Okay, you're doing soon, I believe. Okay.
So typically when you do those titration experiment, you will look something like this. You have a flask, and then you have a solution. So you don't know the concentration of that solution, but you want to quantify. And you want to know the pH of that solution. We call this solution within that flask as analyte. Okay. And for the analytes, it can be any kind of solution. Okay. Strong acid, strong base, weak acid, weak base, and buffer. Okay, so it can be any. Okay, so in your experiment, you need to actually determine the pH of these kind of solutions. Okay. So typically you don't know the concentration. Okay, for your experiment, of course. I mean, for the question we're going to went through is different story. Okay. So what you do is actually you want to actually figure out the concentration of less specific solution. And you want to actually calculate the pH of less solution. Okay, those are typical things you are going to do for your GenChem lab. Okay. So the way you actually figure out the concentration of that unknown substance is that you have a burette. Inside you have another solution. Okay, this solution we call it titrant. Okay, so for your titrant, it can only be strong acid or strong base. Okay, because you want to know exactly how much H plus or OH minus you add it into your flask. Okay, that means since strong acid, strong base, they dissociate 100%, right? So the total concentration is going to equal to your acid concentration. Okay, so it can only be strong acid or strong base. Okay, so this is actually a setup we're actually talking about. One very important concept for titration is that let's say one variable keeps changing. Guess what it is? And you're going to add in your titrant into your analyte, right? So every time you add in something, what's changing? Yeah, pH is changing. Yeah, but that's not the things I'm talking about. Concentration is changing because the body is changing. Okay, so that means every time you see this titration quotient, okay, concentration of your analyte is always changing. That means you always need to recalculate the concentrations. Okay, so that's actually a very important concept that you need to have in mind. Okay, so those are the concepts that you should have before jumping into all the details. Okay, so those are the setup. Okay, now what we're going to do is actually we want to start to define. So remember I said there are 4 different zones, right? So we're going to use one example to tell you how to differentiate zones first. Okay. All right. So this table. Okay, is actually things we want to actually start with. This strong base is our titrant. Okay, so this actually titrant, this actually our analyte. Okay, so when you do the titration, it's always acid titrate base or base titrate acid. Okay, you won't use acid to titrate acid. Okay, so that's why you see inside this table some of the area was actually closed out. Okay. So let's look at this example. A titrate is a strong base. Let's say NaOH. It's a strong base. Okay, that's your titrate. Your analyte, let's say it's a strong acid, meaning we can put HCl. Okay. So the first zone we're going to talk about is what? Before you add any titrate, right? Therefore, under this specific example, what kind of solution are you going to have? A strong acid solution, right? HCl solution. Okay. So you're going to see this curve a lot. It's actually a titration curve, okay? So where the y-axis represents the pH, okay? X-axis represents how much titrate you put into your analyte, okay? So our first law is actually before you add in any titrate, right? Let's say you have 0.1 m HCl to start with. Okay. And the zone number 1, you have strong acid concentration, right? Therefore, your photon concentration will equal to 0.1. Therefore, the pH will equal to 1, right? Negative log 0.1 is equal to 1. Therefore, you know that's actually your first data point, right? pH equals to 1. And I call this one as zone 1. Okay. Before you add in any. Okay. And because it's such a strong acid, therefore your pH will actually below. Let's say this line is a pH 7. Okay. So I guess everybody doesn't have a problem with this. Okay. Strong acid to start with, right? Okay. Now, we're going to enter the zone 2. Okay. Zone 2 is what? You add in your item, in this case, strong base, right? But the amount you add in is actually not going to be outweigh the amount you have for your strong acid, right? So, means that all these OH minus will be filled by the strong acid. Okay. So, your pH will still be, okay, what kind of solution do you have? You still have a strong acid solution, right? Just the concentration of photon is decreasing. Okay. Therefore, the pH will still be low. Okay, so you will see something like this. Okay, it's still low your pH. Okay. But these things will change quickly when you have all this is let's say this is actually my zone 2, right? Where your titrant, the volume of the mole of your titrant is actually still smaller than the mole of your analyte, right? Analyze actually HCl, you still have more HCl inside your solution than your titrant. So that's our zone number 2. You still have a strong acid solution. Right. So to calculate pH of your zone 2 is actually you recalculate what is actually the remaining photon concentration. Right. Once you get that, then you can calculate your pH. Everybody follow the things I say? Okay. Now we're going to enter in zone 3, where you will add base the same amount, right? So we say the strong acid we always use H plus to represent it, right? Strong base always OH minus. When these two they have the same amount, what do you end up with? Water, right? H plus OH minus, they give you water, right? So when you have the same amount of strong acid and strong base, you're actually at your zone 3. Okay. which you only have water, right? Which you know the pH has to be 7 and 25 degrees C. Okay. Therefore, you can see the things actually shows up. This actually will be your zone 3. Okay. And under this case, the more of your titrant and more of your analyte will be the same. Okay. And then the corresponding volume that you add in for your titrant, we actually have a very specific name for it. It's called the equivalence point. Okay, so EP stands for your equivalence point. Okay, so every time you heard this term, equivalence point, it means you have the same amount of titrant in analyte. Okay, so in the strong acid, strong base condition, you can consider that you have the situation H plus your OH minus produce H2O, right? And the H plus and OH minus they consume each other fully, 100%, nothing left. All you have right now is actually just water. Okay, since you have water, therefore you know your pH will be 7. Okay, so far so good. Okay, now think about this. After zone 3 is going to become your zone 4, right? You're going to add in more titrant than all you have for your analyte. Okay, so that's actually your zone 4, which is passing your equivalence point. Under this case, the more of your titrant will outweigh the more of your analyte. Meaning right now more OH minus, right? So OH minus is going to kill all the H plus inside your solution. You still have a lot of OH minus remain inside your solution. Okay, so under this case, what kind of solution are you going to have? A strong base solution. Okay, therefore, you're going to see something like this. The pH, since it's strong base, right, the pH is going to become very high. Okay, so this is actually a curve you should expect when you have your titrant is your strong base. Your analyte is your strong acid. Okay. So if you get back to this, I want to write out what kind of solution I'm going to have for different zones. Okay. What kind of solution do you have for zone 1? What's the solution you're going to have for the zone 1, which is only have your, okay? How about zone 2? Because right now you still have more HCl than your OH minus, right? All the OH minus will be consumed by still plenty of H plus inside your solution. Therefore, you have a strong acid solution, right? How about zone 3? It's neutral, right? What do you have? Is H2O, right? So this is actually a neutral solution. Okay. How about zone 4? Good. Okay. So we're practicing this. It's very important you see this because once you know what kind of solution that you have, all you do is actually calculate your photon concentration. You can actually calculate your pH. Okay. So far, so good. Any questions so far? Okay.
Now we're going to enter the most difficult part of this chapter now. Okay, we're going to deal with a situation
of this.
where I'm going to put the weak acid in my analyte within the class, okay, to start with. And I titrate it with a strong base, okay? Are everybody ready for this solve experiment now? Okay. Zone 1, tell me what kind of solution do you have?
Yes.
We only have our weak acid inside our solutions, right? Therefore, in zone 1,
We know we're going to have weak acid.
zone 2, what kind of solution are we going to have? Okay, so the things I want to see is that we are not starting from H plus. Okay, because it's not strong acid, right? We start from what? HA, right? A weak acid HA. So equation will be HA plus strong base is OH minus, right? So HA plus OH minus is going to produce what?
So HA plus OH minus. We know this guy is going to capture the H plus, right? So once you get the H plus, what's remain? A minus, right? Of course, when this catch land, you got H2O, right? But this doesn't really contribute to your pH. Okay, so you're going to produce this, right? So now, who is actually in acid?
HA or OH minus in zone 2? You have more HA or you have more OH minus? You have more HA, right? If you start from HA, you have a bunch of HA. Okay, you start with a little amount of OH minus. Therefore, your HA is in excess, right? And this OH minus is going to get all the H plus you can get. Okay, but I only have a small amount of OH minus. Therefore, I only get a few H plus from HA. Okay. So under this case,
Inside your solution, this is still the dominant species, right? But once you have these things to happen, you're going to have
increasing amount of A minus 2. Okay. So right now you actually get to a situation where you have your conjugated acid base show up in the same solution, right? So what do you have? A buffer solution. Okay. Therefore, you know in zone 2,
you're going to have a buffer solution.
right? Then to calculate pH of the solution in zone 2, then you use HH equation. All right? Zone 3, you have the same amount, the same mole of your titration analyte, the same mole of weak acid and strong base, right? What are you going to end up with? In your HA have the same amount of your OH minus, right? And they're going to consume each other fully. Therefore, you don't have anything left until that. All the thing you have is what? A minus, right? Which means you have a weak phase solution. Okay? How about zone 4? And zone 4, you're going to have a lot of OH minus and a bunch of A minus, right? But we know strong base is going to dominate and dictate your pH, right? Therefore, you have a strong base
solution.
Okay. So this is actually the key concept that you need to have. Because every time you always need to know which zone you are. Once you know which zone you are, you know what kind of solution that you have. Therefore, you know what equation to use. So let's get to the logic that you must have for chapter 14. Is that clear? Okay. So I also want to draw
The curve for the second equation. Okay, let's say we have 0.1 N CH3 COOH, a weak acid.
okay.
So if you draw all things on this plot, okay, since it is actual, in the beginning you don't add in any titrant, right? In zone 1, you have weak acid solution. Okay, you can compute its pH. Okay, so if you do a simple calculation, you will have a pH around 2 point something.
Okay, so let's get what you're going to have a weak acid as your analyte. Strong base as your titrant at zone 1. You still have a pH below 7. Okay?
And then at the zone 2, at zone 2 we still have buffer, right?
So what it means is that the pH is going to change much, much slower because it's buffered. Okay, buffer doesn't change the pH too much.
Therefore, we're going to see something is actually slow. Okay, and when you hit the VEP, what are you going to have?
What I'm going to have at zone 3, you will be a weak base solution, right? It's a weak base solution at zone 3. Meaning what? Your pH is going to be above 7, right?
So what does it mean? The VEP, you are going to hit
A pH that's above 7. Okay?
I guess this curve is actually not very nice. You should have actually something that's actually relatively stable. And then start to jump. Okay, and when you hit your VEP,
Then you're going to have a pH value higher than 7. Okay.
and then after your zone 3, then it will be again becoming a strong base solution. Okay, so this will be your titrant is a strong base. Your analyte is a weak acid.
Okay. So those are all the things that you need to know for titration. Okay. So I draw the things is I use my titrant is strong base, right? And analyze the two situations, one strong acid, one weak acid, right? Go home and place on the right, where you're going to have a titrant strong acid. Your analyte will be strong base or weak base. Okay, you will be the mirror image of this. Okay.
But I want to actually still summarize the things for you. Okay, let's say if today you have a strong acid as your titrant, okay, and strong base as your analyte. So in zone 1, apparently you're going to have a strong base solution, right? Zone 2, you still have more aniline, therefore you still have a strong base. At zone 3, it will be neutral. At zone 4, it will be strong acid. Okay, so you should see that they are just flipping, right? Strong acid becomes strong base. Okay. Similarly, if you start from a weak base, therefore you know in the beginning you have a weak base to start with. Okay, then after you add in your strong acid, it's going to produce this conjugated acid of your weak base, right? Therefore, you also have a buffer. Okay. At the equivalence point, you have the same amount of strong acid with base. Okay, they're going to consume fully with each other. Okay, therefore, you're going to produce is conjugated acid, right? You have a weak acid. And after your equivalence point, then you have a strong acid again. Okay, so these are the very important concepts that you must know. You're going to do any question. Make sure you understand this. Because if you understand this, when you read the questions, you know immediately know what equation to use. Okay, so recognize this pattern is extremely important. So that's why we spend so much time explaining these things. All right. Okay, so how do you actually know which zone you are? So let's say the one equation that you need to know is called the equivalence equation. Okay, and the way you calculate it is actually very simple, right? You should see that now. It is no difficulty to determine if you are in zone 1. Right? Because zone 1 is actually you don't actually add any pattern. So if you are in zone 1, it's actually very clear. Okay. So now remaining things actually how we tell you actually in zone 2, 3, or 4, right? The way you actually determine this actually need to know under what condition you will be actually in zone 3. Right? If you actually go beyond that, you're in zone 4, go below, you'll be in zone 2, right? So you have to know your equivalence point. You need to know your VEP, right? So the way to calculate your VEP is very simple because we know at VEP, the mole of your titrant is going to equal mole of your aniline, right? So if you know the concentration of your titrant, once we hit my VEP, okay, there will be the total mole you have for your titrant. Okay, and that should equal to a mole of your aniline, which can be obtained from the concentration of your aniline times the volume of your aniline. So this is actually the way, this is an equation that we need to actually memorize, so you can actually calculate the VEP. All right. So we're going to use this one to do a few questions. But first, let's get ourselves familiar with how to use the exchange equation. Okay. So if you read these questions, it says, calculate pH of, list a bunch of things. Okay. And they give you the Ka value of certain things. Right, we're still using our QD pack, right? And the question is going to calculate the pH, right? And then you have a bunch of things you can write out. Okay, you have C6H5 COONA. 0.99 gram. Formula weight 144.1 gram per mole. And then you have C6H5 COOH 0.5 N 32 mil. Okay. I can write out all these things, right? Since you know your calculator pH. The first question you ask yourself is what? What kind of solution do you have? What kind? Can you see this? Every time you see Na, you throw it away, right? Every time you see this 1A elements within a chemical formula, you throw it away. Okay, so this one will become, you throw it away Na plus, which will give you this C6H5, C6H5 COO minus, right? So if you compare these two, what are they? Conjugated acid and base solution, right? What they call solution? It will be a buffer solution, right? Therefore, you know buffer solution. Therefore, you know HH equation. Therefore, your plan will be pH equals to pKa negative log conjugated acid over base. Okay, Ka value is right. So negative log 6.5 times 10 to the negative 5 negative log acid concentration. What's the acid concentration? Okay, so you need to recognize this is your HA, this is your A minus, right? Therefore, acid concentration is actually 0.5. How about your A minus concentration? It is not given, right? Because it gives you a bunch of information here. But we know how to calculate the concentration, right? So the concentration we use in midterm 2 will always be molarity. Okay, so concentration of your C6H5 COO minus will equals to moles over liter, right? The mole will calculate by 0.99 over 144.1. Liter will be volume 32 converted into liter. And once you do that, you can get a value of 0.2147. Then you put it here, 0.2147. Then you can calculate your pH. It's going to equals to, this term is 4.1871, second term 0.3671. Therefore, you got your pH equals to 3.82. Okay, so this is how you handle the calculation of buffer, right? Recap this very quickly is that you first need to know what kind of solution that you have, right? You need to have an eye to see the C6H5COONA is really telling you that I have a C6H5COO minus, right? And then compare that to your C6H5COOH. You know, these two things will coexist inside your solution. Therefore, you have a buffer. Okay, once you have a buffer, then HH equation. Okay. All right. Questions? Okay, so I think this is actually something everybody need to actually know for your midterm too. So So everybody have your periodic table, right? So you have this, you can see all the elements in your 1A or 2A elements, right? So for the 1A, you have what? Lithium, sodium, potassium, so on and so forth, right? If you see any element of that, once it's actually presenting inside your chemical formula, they form a salt. Once you throw it into those into waters, it dissociates. And then 1A group always carries positive 1 charge. 2A group always carries positive 2 charge. Okay, and those things is neutral. So it doesn't contribute to your pH calculation. Therefore, you don't care about that. You can throw them away. That's fine. But the remaining part matters, right? So you have C6H5, COONA. Once it dissociates, it becomes C6H5, COO minus, plus Na plus. Right? This guy dissociates to give you this. So if you look at this, right? So all the atoms need to actually still present it on the product side, right? Charge-wise need to be balanced. You have positive 1. This one has to carry negative 1. So that it's the same on both sides. You start with a neutral molecule on the left. You end up with 2 charged species on the right. The charge of these 2, when they add up, it still need to be neutral. Okay, so this is how you actually convert these things into a C6H5BOO minus. Then you know this one doesn't contribute to your pH, right? So ignore it. So this one is actually things you need to focus on. So once you have this species, and you also see its conjugated acid, right? C6H5, COOH. Therefore, you know you have a conjugated acid base pair inside your solution. Therefore, you have a buffer. Okay. So this is actually one type of molecule you're going to see a lot for the salt, right? The other one is actually what? NH4Cl. This is actually another salt you're going to see all the time. Okay. And for this 7 ACE element, right? The fluoride, chloride, bromide, iodide. Once you throw them into waters, they become negative 1 charged. Right. Therefore, you know the remaining one will be this guy. And this is the one that's going to contribute to your pH. Right. So when I say I'm throwing an NH4 Cl into water, I will be throwing in the solution to my pH is NH4 plus. Right. So if I say I have a solution throwing a bunch of NH3 and a bunch of NH4 Cl. Okay, I'm also going to have a buffer solution. Okay, because I again create a conjugated acid-base solution. Okay, and there will be a buffer. Therefore, use HH equation to calculate the pH. Okay, is that clear? All right, so these are the really fundamental things that you need to know. Okay, you must know this. Okay, otherwise, you'll feel very difficult when you read the questions. I want to actually quickly go through one to tell you how to use the calculator BEP. Okay, so question number 2. A buffer contains 0.45 N of KHCO3 and 0.2 N K2CO3. Given the K value for H2CO3 are Ka1 equals a value, Ka2 equals a value. Oh, this is actually more complicated. You know what? Okay, we'll talk about this later because I feel like if I go too fast, everybody get confused, right? So we'll go through this one again on next Tuesday, okay? And remember, okay, so we're going to spend a lot of time thinking about the titration, okay? This is actually the most confusing part of the whole midterm too. Means this is the part that you need to spend most of your time on, okay? How do we actually make this efficient? Is to recognize the pattern we went through today.
Okay, so you must have a good idea on what kind of solution that you have. So when you go back home this week, really practice left thinking. Because once you have left thinking, you'll be like, okay, you tend to maybe it's like the easiest one that you can take. Okay, it doesn't really take you time to memorize a lot of equations. You will remember majority of the equations when we turn to math. Okay, so now essentially, can you really see what kind of solution that you have? Okay, so always ask yourself this question. All right, and we're going to do more questions next week. Next week, we're also going to enter chapter 15 and finish chapter 15. Okay, chapter 15 is actually the easiest one among the 3 chapters. Okay, so you don't have to worry too much about that. Okay, so right now really focus your energy to understand the 4 zones I'm talking about. Okay, and then if you feel like you step up a little confused, go back and watch my YouTube video talking about the concept. Okay, 4 zones is the key for your midterm too, so do work on it. All right, so that's it for today. Thank you.